Hello everyone, I welcome you all to SS Talks Chemistry. I hope you all are doing great. So we were discussing the previous year questions of the CSIR NET exam, and in that the unit we have started, it was atomic structure and the quantum chemistry, right? So already one of the part of this we have discussed, where some of the questions of this unit we have discussed. If you have not watched, playlist I have made on the channel that includes all the previous year questions of the CSIR NET exam. There that video you can get it. Okay, so now let's begin with our next part, which is your part number 2, where the further questions of this unit we will be discussing. So let's begin. Before starting, if you are coming to the channel for the first time, make sure you subscribe to the channel and do hit the like button also for the video if you understand the concepts, and do share it with your friends as well, because many more such videos are on the way for all of you. Okay, so now this question we are having, this is from the CSIR exam conducted in the June month of the year 2014. The question it says the spatial part of the wave function of the atom in its ground state is 1s1 and the 1s2. What would be the spin part in this? Okay, so the overall wave function that you have, it consists of two of the parts. So the wave function total, it consists of its space part and it consists of its spin part, right? We want that the total wave function, it should be anti-symmetric in the nature. It should be anti-symmetric. That means if the spin part in this, it is your symmetric, the space part it should be anti-symmetric, right? If the space part it is symmetric, then the spin part in this it should be anti-symmetric. Only then the overall wave function we will be getting it to be anti-symmetric, right? So now the given space part of the wave function, it is 1s1 1s2. So psi for the space part, it is given as 1s1 and the 1s2 it is given, right? So now to check that if it is symmetric or the anti-symmetric, so this wave function we are saying that it is psi 1 2 it is there. That means with the 1s1 and the 1s2 it is written, so 1 2 it is there. Now if I interchange this value of this 1 and 2, that means if I write the value of the psi 2 1, so in that case just interchange the first electron with the second and second with the first. If you get the same wave function, then that particular wave function it is symmetric in the nature. Now in this case if you see 1 is with the 1, instead of the 1 here the 2 it will be written, and the in place of the 2 I have to write the 1. So again you see psi 1 2 it is becoming equal to the psi 2 1 only, psi 1 2 it is equal to the psi 2 1 only, which means the space part it is symmetric in the nature, right? Now to make this total wave function to be anti-symmetric, the spin part it should be anti-symmetric. That is the spin part it should be anti-symmetric. Only then the total wave function you will be having to be anti-symmetric, right? So now we will be checking from the given options the spin part which is gonna be anti-symmetric, that is gonna be the spin part which of this particular wave function. So here in the option A if I see, it is alpha 1 alpha 2. Now if I take interchange the position of this 1 and 2, we will be getting alpha 2 alpha 1 we are getting. This it was your psi 1 2, this is your psi 2 1 we can say. So you are seeing no negative sign is coming in front of it. We are getting psi 1 2 is equal to the psi 2 1 only, which implies that this part of the spin it is your symmetric. So this is not gonna be the desired one because we want the anti-symmetric part, right? Now it's similar in the option B if you see, it will become the beta 2 beta 1. So again the same wave function I am getting, so that means again this is your symmetric part, right? Now in the option C if I am seeing, if it is 1 by root 2 alpha 2 beta 1 if you take it, plus of the alpha 1 and the beta 2. So in front of it the normalization 1 by root 2 is as it is. So again you are seeing that both these they are the same only, so that means it is again your symmetric part, right? Now in this one if you see, now it is alpha 1 beta 2, so it will become alpha 2 beta 1 minus of the alpha 1 beta 2. this it is becoming. So this it was your psi12 and this is your psi21. So here if you see psi12 it is equal to negative of the psi21. So if you compare both of this, negative sign has to be taken outside so that you can make the equality in both of this. So if psi12 is minus of the psi21, which implies it is your anti-symmetric part of the wave function, right? That means this is gonna be the spin part corresponding to the space part, which is your 1s1, 1s2. I hope the concept is clear. So option D is the right answer for this one. Okay, moving to the next one, this question. So CSIR December 2014, for a particle which is of the mass m, it is confined in a box of the length L. Assume that delta x value it is L in this. So we have been given delta x value is L. Assume the further that the delta p minimum, which is uncertainty in the momentum we are having, and that was uncertainty in the position. This value it is given as to be p square raised to the power of the half of it. Use the uncertainty principle. So according to the uncertainty principle, according to which we have the delta x into the delta p, this is greater than equal to h upon the 4 pi. This we write it, so we can assume the condition that delta x into the delta p it is h upon the 4 pi, because minimum it has been given for the momentum, right? Next it says use the uncertainty principle to obtain the estimate of the energy of the particles. So how can we find the energy in this? Let's just do this. So delta x value is given as to be L. Delta p value we have been given it is p square raised to the power of half of it, which is equal to h upon the 4 pi of it, right? Now from this value which is of the p square raised to the power of half, if I find it out, it becomes h upon the 4 pi into the L of it. Or we say that the p square value, this is h square upon the 16 pi square into the L square of it. This value we are getting. Now the system is particle in a box. So in this, what you consider, this box it is there, which is of the length 0 to L. The potential inside the box is considered to be 0 and the potential outside the box it is infinite. This is what the conditions we have in the particle in the box, which means the total energy that you have, that is sum of the kinetic energy, which we denoted with the T, plus the potential energy. Now this value of the energy it is 0, right? That means the total energy of the system it is your kinetic energy only, right? And the T is your kinetic energy. This is the kinetic energy, and TE we have written, this is for the total energy. Now the energy of the system, that is the total energy, this value it is equal to kinetic only, which we in terms of the momentum we can write it as it is p square upon the 2m of it, right? Now p square value we have already found this one, so divide this with the 2m and you will be getting the total energy of this particular system, right? So that means total energy it is coming out to be h square upon the 16 pi square, h square upon the 16 pi square into the L square upon the 2m it was there, right, into the 2m of it. Like this we can write it, right? Or we can say it is h square upon the, now it gives us, you can write it as 4 pi square into the L square into the 8m. Like this we can write it. Why I have written it like this? Because h cut, if you see, it is h upon the 2 pi of it. So that implies h cut square, it is gonna be h square upon the 4 pi square. So this value which is of the h square upon the 4 pi square, this you can substitute it with the h cut. So that means the total energy it is coming out to be h cut square. So it is becoming the h cut square upon the 8m L square. right? So these are the two of the formulas. One is this one you are getting, that is in terms of the h cut square, or if it is in the terms of the h square, then this energy values we are obtaining. Now from the options we can match it. So first it is saying h square upon the 8 ml square. This can't be there because when it is in the form of h square, 16 pi square. Now pi square value is also there. So this is not the correct one, right? Next it is h cut square upon the 8 ml square. So here you see in terms of the h cut, it is h cut square upon the 8 ml square. So that makes the option B to be the right one. Similarly, the third option also you see it is h square, but no pi term is included in this, so that's why it becomes the incorrect. Here also it is h square upon the 2 ml square, again it becomes to be the incorrect one. Okay, I hope it's clear. Moving to the next one, this question now, again CSI December 2014. The angular momentum operator, which is your LZ, it is minus of the iota h cut into the del upon the del phi of it. Now what is gonna be the eigenfunction for of the form, which is the which has the eigenfunction of the form. So the wave function of the form, it is given that it is exponential of the iota into the a into the phi of it, right? The conditions that fulfill the at a full rotational level, such as the eigenfunctions it unchanged, is satisfied for all the values of the a in this. So this is the wave function that is given and the Lz is applied over it. So if on the wave function Lz, so you might have learnt about the particle honoring system, where the Lz operator, which is minus of the iota h cut del by del phi, this you apply it upon the wave function. So the wave function, you get the various eigenvalues in this. That is your in the form of the m h cut and the wave function psi we get it. And the energy if you obtain in this for the wave function, energy we are getting it is m square h cut square upon the 2i of it, right? So in that also the wave function, if it is of the form of the exponential of the iota a into the phi, instead of the a, here it is the m value only, right? And for this, from the energy values, if you see here, the for the m value which is 0, this energy value is gonna be non-degenerate. Rest all that, if you take the value of the plus minus of the 1 for the m, or if you take the plus minus of the 2, that means for the plus 1 and for the minus 1, the energy levels are gonna be degenerate. Similarly for this plus minus of the 2, energy values are gonna be degenerate, which implies m possible values are 0, plus minus 1, plus minus 2, plus minus 3, like this the values that will be there, right? So based upon this, option B is gonna be the right answer. Okay, now the next, this question, it says a particle in a one-dimensional box which is of the length L is perturbed by the delta function potential, where the delta value is delta x minus of the L by 2. So that means perturbation has been given to us, which is delta into the x minus of the L by 2. So this perturbation they have applied in a box which is of the length 0 to L. So this is the length of the box. In this the perturbation is applied. In the middle of the box, the first order energy correction to the ground state it is gonna be. So we need to find the energy for the first order in the ground state. This value we know it is gonna be equal to the wave function which is of the ground state, then the perturbation, and then the wave function psi naught as it is. Either in the bracket notation you can write it like this, or this is equal to integration of the psi naught in star into the delta h into the psi naught into the dx of it, because particle in the 1D box only it is there, right? So now here the length it is varying from the 0 to L, right? Now the wave function for the ground state, so ground state it is not the psi naught, it is the E1 in the particle in the box, so you can write the psi 1 over here. Okay, so this is the first order for ground state, so that is psi 1. Here also it is psi 1. So the wave function for that, it will become root of 2 by L into the sine of pi x upon the L of it. So n value is 1 only. Okay, so substitute these values now. So energy correction of the first order for the ground state, it is gonna be integration root of 2 by L into the sine of pi x upon the L into the perturbation, that is your direct delta function into the x minus of the L by 2 into the wave function 2 by L into the sine of the pi x upon the L into the dx of it. Now in form of the direct delta functions, when you have, so here this x value that you are having in this, it is equal to the L value, L by the 2. So this is x value is L by 2, and this x value, it is lying in the range of 0 to L only, right? So that means this integration value, it is gonna be equal to, so the energy correction, this we solve it like, you have to find the product of the psi star into the psi at the x value which is equal to the L by 2, right? This value is gonna be there. So let's just solve this. So the energy correction for the first order in the ground state, it is gonna be the magnitude of root of 2 by L into the sine of the pi x upon the L into, this is the conjugate part of it, next root of 2 by L into the sine of the pi x upon the L of it. Now here we have to put that x value as L by 2. So substitute that, it is becoming 2 by L into the sine of the pi, x value is L by 2, L it was already present, into the sine of the pi by the L into the L by the, right? So this magnitude we have to find. So here you see this L and L is being cancelled out in both the scenarios. It is becoming the sine pi by 2 into the sine of the pi by 2. So sine 90 we know it is equal to the 1 only. So this is 1 into the 1 into the 2 by L. That implies the energy correction of the first order to the ground state, it is my 2 by L. So this is gonna be the answer for this. Okay. So options, if you see 2 by L. So option D is the one that is gonna be your right answer. Okay. Next, this one, the operator S plus minus are defined by, like S plus minus raising or the lowering operators. S plus value is gonna be Sx plus of the iota times the Sy of it, and the S minus, if you see, it is gonna be Sx minus of the iota times the Sy of it. Okay, where Sx and the Sy are the components of the spin angular momentum operator, the commutator value you need to find, which is of the Sz with the S plus of it. So this is gonna be commutator of Sz with the Sx plus of the iota times the Sy of it. So this we can open it. It will be commutator of the Sz with the Sx plus of the commutator of the Sz with the iota times the Sy of it, right? So now solve it. It is Sz with the Sx plus of the, now iota it can come outside, commutator of Sz with the Sy of it. Now here the cyclic system we have to take like this. So here you keep the Sx, then you keep the y direction, and then you keep the z direction, like this you keep it. Now here from the z you are going to the x, so from z we are going to the x, so we are left is with the Sy. So in the clockwise direction we are going, so iota h cut it will come with that. Okay, now next it is Sy, Sz and Sy. So from Sz you are going to the Sy, which means in the anti-clockwise direction we are going, so it will become minus of the iota times the h cut into the Sx of it. This it's gonna be there. Just solve this. Here it is becoming minus of the iota square into the h cut into the Sx. Here the iota times the h cut into the Sy. It was present. The iota square is also the minus of 1 into the h cut into the Sx. Now minus minus will become positive. It will become h cut into the Sx plus here the iota h cut Sy, it was already present, right? So here h cut it will come outside. We are getting Sx plus the iota times the Sy of it. So this is equal to the h cut into the S plus of it. So this is gonna be the answer, right? So h cut into the S plus, option A, it becomes the right answer in this case. I hope it's clear. Okay. Now moving to our next question that we are having, this one. So again, CSIR December 2014 exam. The question, it says a quantum particle with the fixed energy where the E naught value, it is less than that of the potential that we have applied. It is allowed to strike through the four of the barriers separately. So four of the barriers in four of the options has been given. The transmission probability is gonna be maximum. So when the potential barrier it is more and energy it is the less, we have the transmission. So tunneling or the transmission we say it. So the tunneling probability, this value we know it is equal to e raised to the power of minus of 2 into the root of 2 times the m into the v minus e upon the h cut into the length L of it. Okay, so this is the tunneling probability that you get. Tunneling probability is gonna be the maximum if the potential V that you are having, this is gonna be the minimum, and the second scenario it is possible if the L value it is minimum in it. Okay, so here you see, here in the tunneling probability expression that you are having, if V value it is gonna be decreasing, if V value it is decreasing, then E raised to some negative power that you are having, that is gonna be decreasing, which implies tunneling probability it is increasing, right? Similarly the L value, if suppose L value it is increasing, in that overall E raised to some negative power it will be increasing, so in that case tunneling probability it will be decreasing, right? Whereas if this L value we are decreasing, the E raised to the something in the negative power it is gonna be decreasing, right? So that means this value of the tunneling probability that you will be having, that is gonna be increasing because some small value in the negative will be raised to the exponential part of it, right? So these scenarios it will be there. So here the potential V you are having and the length it is 2a over here, right? We have to choose a system where the V value it is minimum and also the L value is minimum. So here this is the value A you are having and here it is the V value which is there, where the tunneling probability we are gonna have the maximum one. Had it been the scenario that the T minimum we have to choose, in that case V maximum you will be choosing and the L also the maximum value you will be choosing, right? That would have been in this scenario which is given in the option D, right? So this is for the T minimum and this one it was for the T maximum. Okay, so B is the answer in this case. I hope it's clear. Moving to the next, this again CSIR December 2014, for some one electron system with the L value equal to the 0 and the M value also equal to the 0, the functions are given, which is n naught e raised to the power of minus of the sigma and the n1 2 minus of the sigma e raised to the power of minus of the sigma by the 2. It refers to the respectively to a ground state which is E naught and the first excited state which is E1 energy levels. So this level is giving me the energy which is the E naught and this level is giving me the energy which is E1. Okay, so if the variational wave function has been considered, so we are now having a trial wave function which is given as n to the 3 minus of the sigma e raised to the power of minus of the sigma. Now this trial wave function it is yielding the average energy value which is E bar. So now this E bar average energy values we have to compare in this, right? So the same state energies you have to compare. Energies can be compared, right? So now from the given state levels, if you see the first level here, this value, if you equate this to be the 0, so in that case, if you keep the sigma value to be infinite, only then this wave function it will become to be the 0. So this is for the ground state, this is for the first excited state, right? This is the one. So this value, if I keep it to be the 0, that value is gonna be 0 if sigma value it is coming us to be the infinite. That means this is your boundary conditions only. This is my boundary condition. That means the node in this it is 0. So that means this state it is having the 0 node, right? Whereas the psi1, if you see, you equate this complete wave function to be equal to 0. That thing is possible if you keep the sigma value equal to the 2, or you keep the sigma value as infinity over here, right? So again, this value is gonna be infinite, that is gonna be at the boundary. So this can't be there. This is the boundary. That means the node is present only at this particular position. So number of the nodes in it, it is your 1. Right? Now the given trial wave function, here also if I see this wave function, it is gonna be equal to 0 if the sigma value it is equal to the 3. Only then this wave function will be 0, which implies in the trial wave function also one node it is present in it, right? So in the trial wave function one node is present, so its energy it will be compared to the level where the one node it is present. That means psi trial will be compared with the psi 1 node, right? Now energy for the trial wave functions that you obtain, it is always greater than or it is equal to the one which is of the same state, that is your E1. So this is gonna be the relationship between these energies. Okay, so main thing was same states energy you have to compare, and for the trial wave functions, trial energies, it is greater than or it is equal to the exact one. Okay. So this scenario you are having E bar is greater than that of the E1. So option C that is given, it will be the right answer in this. Okay. Next, this question, CSIR December 2014 again. A Slater determinant corresponding to the ionic part. So ionic part means both these electrons on the same part, same atom. Both electrons on the same atom we have to consider. Had it been the covalent, in that case there will be the sharing of the electrons. Sharing of the electrons, which means one electron on one of the atom and other on the second one. Right? So here now the ionic, both the electrons on the same part of the hydrogen molecule. So now the hydrogen molecule, it means two of the atoms you are having. This is your Ha, this is your Hb. These are their nucleuses, and two electrons these are involved in it, right? So this scenario is given is 1s A alpha, 1s beta, 1s alpha, and the 1s B beta has been given are the atomic spin orbitals of the hydrogen atoms A and B of the hydrogen molecule. So from the given Slater determinant, you have to predict which one is showing you the ionic part in this. So firstly, if the option A, if I consider, it is showing 1s A alpha 1, 1s B, 1s A beta 1, right? Next it is 1s A beta 2. Similarly here it is 1s A alpha 2 it is given. So open this determinant. We will be getting cross multiply like this. Diagonally you have to multiply it. It will become 1s A alpha 1 into the 1s A beta 1 beta 2 it is given, right? Minus of 1s A beta 1 into the 1s A alpha 2 it is given, right? So here you see in the brackets these denotes the electron. So this is your first electron which is present on the atom A. This is your second electron which is present upon the atom B, right? Similarly here you see first electron on the atom A and the second electron on the atom A only. Both this they are denoting the ionic parts only. So this is the one which is showing the complete ionic part. So option A is only the right answer. You can check the others also. I'll be showing beta 1, this beta second one, that option you are having. So B option it is 1s A, 1s A, alpha 1, 1s B, beta 1. This is 1s B, beta 2. Here it is 1s A, alpha, right? So open this, it will become 1s A alpha 1 into the 1s B beta 2 minus of the 1s B beta 1 into the 1s A alpha 2, right? So here now if you see, it is saying the first electron it is on the atom A, the second electron it is on the atom B it is showing, which means it is the covalent part, right? Similarly The first electron on the atom B, the second electron is on the atom A. Again, it is representing the covalent part. So it is representing the complete covalent part in this, right? Similar way you can check it for the C option. It will become this one. I'm writing it over here. 1s A alpha 1 into the 1s B alpha 2. You are having minus of the 1s B alpha 1 and the 1s A alpha 2, it will be there, right? So here if you see, compare this, first electron is on the atom A, the second electron is on the atom B. Again, this is representing the covalent part. Here also first electron on the atom B, second electron on the atom A, again the covalent part, right? Similarly, the option D also we can check it. So D1 it will become 1s A alpha 1 into the 1s B beta 2 minus of the 1s B beta 1 into the 1s A alpha 1. So here again if I see, the first electron is on the atom A, the second is on the atom B. So that means this is representing the covalent, right? Here also the first electron on the atom B, the first electron on the atom A. So both these electrons, they have written 1 and 1 on the, this is on the B and this is on the A only. So again you cannot say that this is your ionic part. Again we can say this, we cannot say anything about this portion. So here also you see, in this complete wave function, if I am saying covalent part is that. So again this cannot be the answer. So purely ionic, that is in the option A only. Okay. Next, CSIR June 2015 now. It says a particle in a one-dimensional box. So we are having a particle in the 1D box that looks like this. The length of the box is 0 to L. The potential inside it is 0 and the potential outside it we consider it to be infinite to prevent the tunneling of the particle. Okay, inside a box and outside the box it is there. An energy state which is corresponding to n is equal to 0 is not allowed. Why is it so? So in this particle in a box system, the energy value that you get, it is n square h square upon the 8 ml square of it, and the wave function in this that you have, it is root of 2 by L sine of the n pi x upon the L of it. For any of the nth state, these are energies and the wave functions. In this we say that the n value, it is starting from the 1 2 3, like this it is going to the higher levels. N value is not equal to 0. Reason for that it is because if you take the n value as 0, psi 0 you will be having, it will become root of 2 by L into the sine of the 0 pi x upon the L. So this is becoming the root of 2 by L into the sine of the 0, and sine 0 we know it is already equal to the 0 only, which implies the wave function in it, it is becoming to be the 0. So if wave function is 0, how can you find the probability of existence of the particle? How will be finding the energy or the momentum of it? Right? So that is why the n value is not equal to 0. It is not possible. So first is saying total energy, it becomes 0. That's why we are not considering. This is not the case. Average momentum, it becomes the 0. This is also not the scenario. The wave function, it becomes 0 everywhere. So the most opt one is the option C in this case. Okay. Next. This question, it says an eigen state of the energy which satisfy the Hamiltonian operator is applied upon the wave function psi n. This is giving me the energy En and the wave function psi n as it is. In the presence of the extra constant potential, which means a perturbation suppose you have applied, which is your V naught. So in that case, what is gonna happen? So in the tunneling you have seen it, there also this potential it was applied. So the tunneling value that you were getting, it was e raised to the power of minus of 2m times the v minus of the e upon the h cut into the L value we were having. So here the term of the v minus e, it is arising, which implies the energy value, it is changing in it. The energy it changes, but the wave functions, if you see that the wave function, it is not gonna change. It is not changing. It is not changing. Based upon this, it is saying both the En and the Psi will change. This is the incorrect. Both of this En and the average kinetic energy will change. No. Only the En it will change, but not the wave function. Option C is the right answer for this. Okay. Moving to the next one. This question. The simplest ground state valence bond wave function for a diatomic molecule like the HCl is written by. So HCl bond is formed by the overlap of the orbitals of the hydrogen atom, which is the 1s, and the 3p orbital of the chlorine it is there. Right? Now according to the valence bond, that means the covalent character we have to prove in them. One electron on one of the atom, the second on the other one. Like this, you will be having the first, which is the phi A, upon this the first electron into the phi B, which is the second, which is containing the second electron, plus the possibility. Now bonding we are considering here, you see it is the ground state. So ground state, it means the bonding will be there. It is the bonding molecule, bonding orbital you will be having. So this will be including the phi A, which is containing the second electron, into the phi B, which is containing the first electron. Right. So now here instead of the phi A, we have the orbitals of the hydrogen and the chlorine. So it will be phi, which is of the 1s orbital of the hydrogen atom containing the first electron, and the second, which is the 3p z orbital of the chlorine, which is containing the second electron, plus of the phi of this 1s orbital of the hydrogen containing the second one, and the 3pz containing the of the chlorine atom containing the second electron. And like this we will be writing it. Okay, based upon this, the options if you see, so it is saying the wave function instead of the phi they have used is now psi over here. Just this difference it is there. For the hydrogen atom it's 3pz. So is the hydrogen 3pz contributing? It is the incorrect. Right. Next it is hydrogen atom, it's 1s orbital. This is the one containing the second electron, and the chlorine atom it's 3pz containing the first electron. This is gonna represent the covalent character. Right. Best options also you can say. Here it is chlorine with the 1s, that is not possible. Next chlorine, its 1s orbital is overlapping with the 3pz of the hydrogen. This is also the incorrect one. Okay, so option B is the right answer for this one. Okay, next this one now. Which of the following statements is incorrect? Incorrect you have to choose. It says the slated determinant is the anti-symmetricized wave function. This statement is the true one because total wave function that we used to write, we consider it to be anti-symmetric, and slated determinant is able to prove that. Right. Next, the electronic wave function, it should be represented by the slated determinants. This is also the correct. A slated determinant always corresponds to a particular spin state. This is the incorrect one. So it basically represents the, it is not representing a particular spin states, it represents all the spin states. It represents all the spin states. Like for the triplet also you can have it, and also for the singlet. Singlet also, and for the triplet state also the slated determinant is able to, we are able to draw it. Right. So this statement is the incorrect. Option C is the right answer. Right. Fourth statement, it is saying it obeys the Pauli's exclusion principle. This is also the true one. So C is again the right answer in this case. Okay. Next, CSIR June 2050, 2016 it will be, I guess, or it's 15 only. Okay. So compare the difference of the energies of the first excited and the ground state. So make sure you read the statements very carefully. The difference is energies of the ground states and the first excited state of a particle which is confined in a 1D box, which is having the delta 1. Difference is shown, a 2D square box and a 3D cubic box. So we have to tell the relationship between these, all of this. Okay. So firstly, it is the 1D box, which means only one direction. The particles axis we are considering. So wave function will be also the psi x only, which is root of 2 by the lx into the sine of the n pi x upon the L of it. Energy corresponding to this we get, that is n square h square upon the 8 ml square. Right. Now here the n values, it is gonna be 1, 2, 3, like this it goes on. So the various energy levels if we draw in this, the ground one, that is when the n value is 1, energy corresponding to it is gonna be h square upon the 8 ml square, right? Now the first excited state, that means when n value is 2, energy will be 4h square upon the 8 ml square, right? Difference between these two, this difference, this they have said it to be the delta 1, that is coming out to be 4 minus of the 1, which is your 3h square upon the 8 ml square. So this is the delta 1, energy difference between these two levels, right? Now similarly for the 2D box, if you see, which means two of the directions they have considered, wave function it is along the nx and it is along the ny. Wave function it is multiplicative, that is gonna be root of the 2 of the lx into the sine of n pi x upon the lx. Here also this x it will be there into the root of 2 by l into the, this is along the y direction, sine of the ny pi of the y upon the ly of it. This is the wave function. Now the energy in this case we obtain, which is additive. So energy along the x plus along the y you have to add it. So this is gonna be nx square plus into the h square upon the 8 ml square plus of the ny square into the h square upon the 8 ml square. Because the length is the same, so lx is equal to the ly. This condition has been given in the square box, right? So energy will be nx square plus of the ny square into the h square upon the 8 ml square of it, right? So here again the nx ny values, if you see, nx ny values it starts from the 1 2 3 like this it goes on. Now for this the various energy levels, if I see the ground one, where the 1 and the 1 value of the nx and the ny we will be having, energy it will be 2h square upon the 8 ml square of it, right? The next higher level it is gonna be doubly degenerate, where if you can keep the values of the nx to be the 1 and ny to be the 2, or you can consider the nx to be the 2 and ny to be the 1 in this. These both are gonna be degenerate, that means the same energy it is gonna yield. So if you find the energy, it is gonna be 5h square upon the 8 ml square of it, right? Now the difference between these two levels it is delta 2. So here the difference, if I see, 5 minus of the 2 h square upon the 8 ml square, right? So that is again coming out to be the 3h square upon the 8 ml square of it, right? So this value is also the 3h square. Now for the 3D box, so wave function it is along the nx, ny, ny and the nz of it. This value it will be there, it will become root of 2 by l into the sine of the nx pi x upon the l of it. Lx, ly and the lz we are considering it to be the same only, their length is same because it is in the cubic box, right? Next it will be root of 2 by l into the sine of the ny pi of the y upon the l of it into the root of 2 by l into the sine of nz pi z upon the l of it. This is gonna be there. The energy value that you observe in this, it is the sum of the energy along the x direction plus the y direction plus along the z direction. That is nx square plus the ny square plus of the nz square into the h square upon the 8 ml square of it. Again nx, ny and the nz it starts from the 1. So the lowest level of the energy it is gonna be 1 1 and the 1. The energy corresponding to this we get, which is 3h square upon the 8 ml square of it, right? The next level which is gonna be your 1 2 1, or we can consider the 2 1 1, or we can consider the 1 1 2. So here all these three are gonna be degenerate, that is gonna give the energy which is 1 square plus 2 square, 4 plus 1 is 5, 5 plus 1 is 6, so 6h square upon the 8 ml square of it, right? Now this gap between these two levels, this is the delta 3, that is again coming out to be 6 minus of 3 into the h square upon the 8 ml square of it. So that is equal to 3h square upon the 8 ml square. So this is the gap that we are obtaining. So here you see delta 1x, delta 1 that we have obtained, it is 3h square upon the 8 ml square. Delta 2, it is also the 3h square upon the 8 ml square. And the delta 3 also you have obtained it to be the 3h square upon the 8 ml square. So we can say that delta 1, it is equal to the delta 2, it is equal to the delta 3. Their magnitude, it is 3h square upon the 8 ml square of it, right? So options, if I see, first it is saying delta 1 is greater than the delta 2 than the delta 3. Incorrect. All of these three, they are equal. Option B is the right answer. Okay. Next, CSIR June 2015 again. The correct statement about the average value of the position and the momentum of a 1D harmonic oscillator. We know this in the 1D SHO. The average value of the x is 0 and the average value of the momentum also, it is the 0 only. So option C, that is x is 0 and delta this average value of p is 0. Option C is the right answer. Okay. Next, CSR June 2015 again, the commutator of this, which is x, commuting with the commutator of the x with the px of it. Okay, so now I know if x commuting with the px raised to the power of n. So this is generalized only for the position and the momentum formulas. This is gonna be n into the px raised to the power of n minus 1 into the iota h cut of it. Similarly, if it is px raised to the power of n and then the x you are having, it is minus of the iota h cut into the n x px raised to the power of n minus 1 of it. Okay, if it is x raised to the power of n into the px, the value is n x raised to the power of n minus 1 into the iota h cut of it. Similarly, if it is px and then the x raised to the power of n, we get the minus of the iota h cut into the n x raised to the power of n minus 1. So if px is in the front, so that is these terms, it becomes the minus of the iota h cut. Rest the derivative part only, because it is x raised to the power of n. So d by dx of the x raised to the power of n is nothing but the nx raised to the power of n minus of the 1. So like this you have to remember, but this is only for the position and the momentum. Okay, that too in the same directions. Okay, so now here the value, it is firstly this commutator x and px that you are having. Now px is after this one, so here it is raised to the power of 1 only, so it will be 1 px raised to the power of 1 minus of the 1 into the iota h cut of it, right? This is the commutator. Now further this commutator we have to find it with the x. So x will be commuting with the px raised to the power of 0, that becomes the 1 only, so it will be commuting with the iota h cut. Now iota h cut, this value is a constant, right? So now operators commutator with the constant, this is gonna be 0, right? So option D, it becomes the right answer. Why it is coming out to be the 0? You can see this x commuting with the iota h cut, it is there, right? So commutator of the a and the b operator, what you have it, this is nothing, first the a and then the b minus of the b into the a. This is the value of the commutator. So now here this formula, if I apply over it, it will become x into the iota h cut minus of the iota h cut into the x only. Iota h cut is the constant, so it will come outside. We are left with x minus of x, which is coming out to be 0. That is why with the constant, this commutator value is 0. Okay. Next, CSIR December 2015 now. It says two different non-zero operators A and B we are having. It satisfies this relation, which is of the A commutator plus of the B commutator into the A commutator minus of the B commutator. This value is equal to A square minus of the B square in which of these scenarios? Okay, so here if I see A plus of the B into the A commutator minus of the B commutator, right? Open this. So A commutator into the A operator into the A minus of the B plus of the B into the A minus of the B. This it will become. So it will become the A operators square minus of the A operator into the B operator plus of the B operator into the A operator minus of the B operators square. That means A square minus of the B square plus of the B operator into the A operator minus of the A operator into the B operator, right? So this will be equal to the A square minus of the B square only if this term, which is B operator into the operator minus of the A operator into the B operator, is equal to the 0, or we can say that A operator into the B operator minus of the B operator into the A operator is 0. So either of these scenarios. A third in the form of statement also we can write it, that if A and B, they are commuting with the one another. A and B are commuting with the one another. One another. So in that scenario also, this thing it is possible. Okay, based upon this, the option A, if it is saying that if AB is equal to the A square and AB is equal to B square, in that case we are not gonna get it. Next, AB plus BA is 0. No, AB minus of the BA was 0. So here it is A and B are arbitrary. Again, not the one. AB minus of BA is 0. Option D is the right answer. Okay. Next, the degeneracy of an excited state of a particle in a 3-dimensional cubic box with the energy which is 3 times of its ground state. So now particle is in the cubic box, right? That means all the 3 directions will be included. Energy for this, it will be the sum of energy along the x plus along the y plus along the z. That is gonna be nx square into the h square upon the 8 ml square plus of the ny square into the h square upon the 8 ml square plus of the nz square into the h square upon the 8 ml square of it. That becomes your nx square plus the ny square plus the nz square into the h square upon the 8 ml square of it, right? So now here this nx, this value nx, ny and the nz, these values, these are possible to be 1, 2, 3, like this, the higher values they are possible in it, right? So now the lowest energy, lowest level, the nx is equal to the ny, this value is equal to the nz, which is your 1 only. So energy corresponding to that you get, which is your 3h square upon the 8 ml square of it, right? Now the energy we are having, which is 3 times of this, 3 times of this ground state energy. This you can say it is of the ground state. Okay, so that becomes the 9h square, because 3 into the 3h square upon the 8 ml square of it. So that is gonna be 9h square upon the 8 ml square of it. That means this value is now equal to the nx square plus the ny square plus of the nz square into the h square upon the 8 ml square. On comparing these two, you see we are getting this sum of the nx square plus the ny square plus the nz square. This is equal to the 9. Now you have to choose arbitrarily the values of the nx, ny and the nz, so that you are getting their sums, their squares of the values is equal, and their addition is giving me the value which is 9. So if I take the nx as the 1, so it is 1 square plus of the 2 square, that is 4 plus 1 will become 5, and here also this 2 square, if I am taking the value, I am getting it to be the 9. So that means first level that is possible, it is 1, 2 and the 2, right? Next way, if you take it, this value as the 2, this value you keep it to be the 1, this again you are keeping it to be the 2, again it is gonna be 9. That means the energy level possible, it is 2, 1 and the 2, right? Next, if it is 2 square plus of the 2 square and plus of the 1 square, so again this is coming out to be a 9, which implies the level will be 2, 2 and the 1. So these three levels we are having, which is gonna give me the same energy, which is thrice of the ground state energy. So we can see from here that degeneracy is 3 in this case, right? So options, if I see, option A only it is given that degeneracy is 3 in this. Okay. Next, this question now, the sp hybrid orbitals. So firstly it is the sp. So percentage of the s, it means how much it is there, that is 1 by 2 of the 100, and the percentage of the p also, if you see, it is 1 by 2 into the 100. So equal percentage of both of this, which is 50, and the 50% that is in the sp hybrid orbital. Okay, so this is written in the form of the wave function, which is c1 2s plus of the c2 and the 2p z of it. So 1s and 1 pz orbital they have taken, 2 at 2s and the 2pz, they are the normalized individually. So these are normalized wave functions. The coefficients of the normalized form of the above sp hybrid orbital, it is gonna be. So the normalization which is of the wave function c1 2s plus the c2 into the 2pz. For the normalization, your c1 square plus the c2 square, it should be equal to the unity. This condition it should be satisfied. Now from the options, if I see, option A it is given c1 value it is 1 by the root 2 and the c2 value is 1 by root of the 2. So c1 square, which is 1 by the root 2 square of it, plus of the c2 square, which is again 1 by the root 2 square of it, which is gonna be 1 by 2 plus 1 by 2, that is coming out to be the 1 only. So this scenario it is possible. So option A only it is showing that these wave functions, their values are also the equal one. c1 square is equal to the c2 square also. c1 square is equal to the C2 square, which means the probabilities also P1 is equal to the P2 only. 50-50% conditions is also being satisfied, and this scenario of the normalization, which is C1 square plus C2 square, is also equal to the 1 only. In the other options, if you see, you are not gonna get it to be the unity. Here if I see, it is 1 by 2, so square of it will become 1 by 4, again 1 by 4, this is coming out to be 2 by 4, which is not equal to the 1. This is not normalized. Similarly for this, if you see, it will be 1 by 2 plus of the 1 by 4. So here it will be coming 3 by the 4, it will be coming. That is again not equal to the 1. And in the option D also it will be 1 by 4 plus the 1 by 2. That is again gonna be 3 by 4, which is not equal to the 1. Right? So option A is the most opt answer in this case. Okay. So moving to our next question now, that is this one. Again, CSIR December 2015, a certain two-level system, it has the stationary state energies, which is E1 and the E2. So two of the levels with the energy E1, and this is the E2. The value it is given that E2 is greater than that of the E1 with the normalized wave functions, which is phi1 and the phi2. So the wave function that has been considered, it is C1 phi1 plus the C2 phi2 of it. Okay, this is the wave function. In the presence of the perturbation V, the second order energy correction to the first state will be. Okay, so energy correction for the second order, which we write it like this, for any of the nth state, this is equal to summation of, where n it is not equal to the m, then in the bracket notation we write it the wave functions, that is m, then the perturbation you apply it, and then the wave function psi n, then we close it, and we take the square of it and divide this with the energy difference, that is of the En naught minus of the En naught of it. This is how we define that. Now for the first state we have to define, so delta E for the of the second order correction in the first state we are applying, so that is gonna be equal to phi 2, then the perturbation, which is the delta H, and then the phi 1, it will be there. You take the square of it upon the E1 minus of the E2 of it. This value we will be getting. Based upon this, the options, if you see, Here the no square term is not included, so this can't be the one. Here also the square term is not there. This is the incorrect. Here the square term is included, so, and the difference is of the E1 minus of the E2. But one difference here you are seeing, here it is phi1 and then the phi2 has been written. In our expression we have written phi2 and then the phi1. Okay, so this we can consider it for a while. The option D, if you see here also they have taken to be the square, here also they have taken to be the square. This is also the incorrect one, right? Because the second order energy correction that you have, second order correction that we obtain, this is negative always for the ground state. This is negative for the ground state. The scenario is always that. The reason being, this difference which is of the E1 minus of the E2, that comes out to be the negative E1 minus of the E2. Now it's already given that E2 value it is more and E1 value is gonna be the lesser one. So this difference it should come out to be the negative. By squaring of it, it is coming to be the positive. So that makes the option D to be the incorrect. Okay. Now this thing about the interchange of this wave functions, here you are seeing we are having the squares of this and also squares of it is there. So that means this way also we can write it, which is phi1 and then the Hamiltonian and then the wave function which is the phi2 only. So because the square term it is there, here also it will be E1 minus of the E2. Okay, so that makes the option C to be the most opt answer in this case. Okay, next, the radial part of the hydrogenic wave function, it is given as R, which is alpha minus of the R e raised to the power of minus of the beta R of it. This function is then identifiable as. So we have to see that this radial part of the hydrogenic wave function which is given, it is corresponding to which of the given orbitals. So firstly, let's find the radial nodes in this. Radial nodes we have to find. So for that what you do is keep the radial part of the wave function equal to the 0 and find the values of the r where you are getting this radial part of the wave function as 0. Okay, except the boundary conditions, the the conditions that we are getting, that represents the position of the nodes, right? So that means r of the alpha minus of the r e raised to the power of minus of the beta. This value is gonna be 0 if the r value we equated to be the 0, or we keep the r value as the alpha and this third value which is the r is equal to the infinity if you are keeping it. Okay, so these two conditions which is r equal to 0 and r equal to infinite, both these are your boundary conditions only. These are your boundary conditions, whereas r equal to alpha, this represents the node position. That means when you keep the r value as alpha, at that point the radial part of the wave function will become 0 and we will be getting a node over there. That means in the given the wave function, one node it is present, right? Now from the given orbitals which is of the 2s, we are having firstly number of the radial nodes, it is n minus l minus of the 1. This is the number of the radial nodes. So let's check in the given orbitals. So here it is firstly 2s. So n value it is 2. L value it is gonna be 0 minus of the 1, because for different orbitals which is s, p, d and the f, the L value it is 0, 1, 2 and the 3, right? So it is giving me the radial nodes which is the 1 only. Now let's check for the others also. It is 3p, next one is. Now for the 3p radial nodes, it is gonna be 3 minus 1 minus 1. Again the 1 radial node I am getting. Next for the 4d, next is 4d, again 4 minus of the 2 minus of 1, again the 1 node we are getting. Next 5f it is given, so 5 minus of the 3 minus of 1, again the 1 radial node we are having. So that means from the concept of the radial nodes I am not able to solve this question, right? So what I do is I find out the angular nodes in this. I find out the angular nodes in this. So how do we find the angular nodes? From the value of the L in this. So we know that the generalized formula for the radial parts, it is proportional to 2zr upon the Na naught raised to the power of L, e raised to the power of minus of the ZR upon the Na naught. This is the radial part. Now the given part we are having it as R into the alpha minus of the R into e raised to the power of minus of beta R. Compare both of this. So here you are having R value is raised to the power of 1 in this, that is corresponding to the L value. So that means L value is 1 in this. This is the radial node, which this is the angular node which is present. L value is 1, it means it is corresponding to the p orbital, right? That makes from the given options the p orbital it is given us to be in the option B, which is your 3p. So option B will be the right answer in this. Okay. Next, the normalized state phi is constructed by a linear combination of the ground states, which is psi naught, and the excited state, which is the psi and psi 1 for the of some harmonic oscillator with the energy values as 1 and the 3 by 2 units respectively. So what they are saying, the phi value that you are having, it is constructed of the linear combination of these wave functions, which is psi naught and the psi 1. So variational parameters I can add in this, the average energy, this energy corresponding to this, the first one that you are having, so this we can write it as C naught, and this we can say it is the C. So energy corresponding to this, they are saying it is 1 by 2, and the energy corresponding to this one it is given, which is your 3 by 2. Okay, if the average energy that of the wave function, which is your trial wave function, that is also given, which is your 7 by 6, what is the probability of finding the psi naught in the 5 wave function? Okay, so we know that the average value of the energy it is C1 square into the energy C naught square into the energy which is of this particular state plus of the C1 square into the energy which is of this particular state, right? Along with this, we have one of the scenario that this wave function it should be normalized wave function, which is C1 square C naught square plus of the C1 square, it should be equal to the unity. So these two conditions it should be satisfied. Now from the energy values, firstly if you see, we will be having the average energy which is 7 by 6. This is gonna be a C naught square into the energy value of this state which is 1 by 2 plus of the C1 square into the energy which is your 3 by 2 in this, right? So let's take the LCM, which is your 6 in this case, so it will become 3 C naught square plus of the 9 C1 square, which is equal to the 7. So this is the first equation we are having, right? Next one we are having, which is C naught square plus of the C1 square, their sum it is equal to the 1 from the condition of the normalization. So this is the normalization condition. Okay, so now here if you see, if I multiply this with the factor of 3 and subtract both of this, so we will be getting these two, they will get cancelled out, we will be left as with 9 minus of the 3, which is 6 C1 square, this is equal to 7 minus of the 3, which is equal to the 4. So that means C1 square, that will be equal to 4 by 6, right? So this is the value. Now a C naught we can find it, C naught square it is equal to 1 minus of the C1 square of it, so it will be 1 minus the 4 by 6, which is coming out to be as 2 by 6. So this is the value which is of the C1 square, and C1 square, sorry, C naught square. So C naught square is nothing but the probability P naught only, that means the probability of finding the psi naught in the trial wave function, which value is equal to the 1 by 3. So this will become the 1 by 3 only, right? So this is gonna be the probability, right? So that makes the option B to be the right answer. Okay, I hope it's clear. Now the next, this one, it says the eigenfunctions of the Hamiltonian of the harmonic oscillator are the kinetic energy and the potential energies we has been given, where T and V are the kinetic and the potential energies. So what they are asking is that the eigenfunctions of the Hamiltonian, whether they are the eigenfunction of the kinetic energy or the potential energy or both of this or neither of this. So how can you check it? You find the commutator values in this. So here if the two operators they are commuting, if the two operators they operators commute, they have the common set of the eigenfunctions. They have common set of the eigenfunctions. Eigenfunctions, which means the eigenfunctions of the H, it will be the eigenfunctions of the kinetic energy if it is commuting with it. Hamiltonian is commuting with the kinetic energy. Similarly, the eigenfunctions of Hamiltonian will be the eigenfunctions of the potential energy if the potential energy and the Hamiltonian they both are commuting with the one another. Okay. So firstly, let's see it for the Hamiltonian with the potential energy. Firstly, let's see it. Right. So now the Hamiltonian we know it is sum of the kinetic energy plus the potential energy. This sum it is commuting with the kinetic with potential energy or not. Let's see this. So this is gonna be equal to kinetic energy commuting with the potential energy plus of the potential energy commuting with the potential energy. Now operators they commute with the oneself and its powers. So this value is gonna be 0. Now I have to check it for the kinetic energy and the potential energy. Okay. So now the system we are having, which is your harmonic oscillator, right? So in the harmonic oscillator, the potential value that I have, it is the half kx square, right? And the kinetic energy we know it is px square upon the 2m, right? So this thing we are gonna make use now. So here we will be having px square upon the 2m. Commutator we have to find it with the half of the kx square. So with this we have to find it out. So here if the constant values we can take it outside, so it will be half of the k into the 1 by the 2m into px square and the x square. So this value we have to see that if it is coming out to be 0 or not. So it will become 1 by the 4m upon k upon the 4m. Now here this commutator it will be px, then the px commuting with the x square plus of the px and the x square. The px square you are applying it px it will be applied outside, right? So commutator of px with the x square it is equal to the 2x into the minus of the iota h cut of it. This outside at px it was already present plus of the again minus of the iota h cut into the 2x, and after this the px value we are having, right? Along with this constant values they are present outside. So k upon the 4m, right? So we will be getting here. You can take the things out. Minus of the 2 iota h cut minus of the 2 iota h cut outside. So minus of the 2 iota h cut into the k upon the 4m. We will be getting px into the x plus of the x into the px of it. These values they are not equal or it is not equal to the 0, which implies the Hamiltonian with the kinetic energy it is not with the potential energy it is not commuting. So that we can say the this commutator of the Hamiltonian with the potential energy it is not equal to 0. That means the Hamiltonian and the potential energy are not having the common set of the eigenfunctions. Common set of the eigenfunctions. Right? Now similarly we have to find the commutator which is of the Hamiltonian with the kinetic energy. So that is gonna be the sum of the kinetic energy plus the potential energy with the kinetic energy. This will be kinetic energy with the kinetic energy plus of the potential energy with the kinetic energy, right? This commutator, so t with the t it is gonna be 0 because operators they commute with the oneself and its power plus of the potential energy with the kinetic energy. Again this system is your 1D SHO you are having. So potential energy is half of the kx square and the kinetic energy it is gonna be px square upon the 2m. right? So these values we will be making use. So it will be commutator of the half of the kx square with the px square upon the 2m of it, right? So it will come 1 by 2 into the k into the 1 upon the 2m, the commutator of this x square with the px square, right? So it will become k upon the 4m. Now here the x commuting x, I'm keeping it outside, x commuting with the px square, it will be there, plus of the x commuting with the px square, the second one it will be placed outside the bracket, right? So this will become our k upon the 4m. So we will be having k upon the 4m. Now solving this, it will become x into the 2px and the iota h cut of it plus of the, now here it will be 2px into the iota h cut into the x of it. So this is becoming, so here 2 iota h cut, from all of this it will come common. So 2 iota h cut into the k upon the 4m into the x into the px plus of the px into the x. So this is what we are getting. So again this value x px into the px x, this is not gonna give me the sum as 0. So this is not equal to our 0. That means the Hamiltonian is not commuting with the kinetic energy also. So we can say that Hamiltonian and the kinetic energy, they are not commuting. They are not commuting. Hence they do not have the, hence they do not have the common set of the eigenfunctions. Do not have the common set of the eigenfunctions. Right? So that means we can say that neither it is the Hamiltonian with the kinetic energy nor it is with the potential energy. It is not commuting, then the eigenfunctions are the eigenfunctions of the Hamiltonian are neither the eigenfunctions of the kinetic energy nor that of the potential energy. So option D, it will be the right answer. Okay. Next, this question now, CSIR June 2016. The question it says, for a particle of the mass which is confined in a rectangular box with the sides which is 2a and the a. So rectangular box you are having, this is the box. The two different lengths we are having. This length is 2a they have given and this length is the a and this. The energy and regeneracy of the first excited state. So what is gonna be the energy value in this? That is along the x and along the y direction. Energy, it is additive in the nature. So it will be nx plus the energy along the y direction, right? So this it will become nx square into the h square upon the 8m. Now L is here a, so a square you will be having plus of the. Now along the, so here along the x-axis we are having the length which is 2a, so it will be 2a square, and along the y direction it will be ny square into the h square upon the 8m into the a square. Right? So from this we can say h square upon the 8ma square is coming common from both of this. So it will become nx square upon the 4 plus of the ny square into the h square upon the 8ma square of it. This is gonna be the energy value. Now assume the values of this nx and the ny. Now here it is a rectangular box. The minimum value of the nx, ny, it is gonna be 1, 1, 1, like this we will be having it. So firstly, lowest energy it is gonna be the one which is 1 1. So the energy in this it is becoming 1 by the 4 plus of the 1 into the h square upon the 8m square, which is my 5 upon the 4 into the h square upon the 8ma square. Right? 5 by 4 into the h square upon the 8 Ma square. So this is the ground state. We need is the first excited state. So now the higher level possibility is either we can have the 1 2 or it is 2 1. And now among these two we have to select the one which is giving us the lower energy, that is gonna be the first excited state. So if you take Nx as the 1 and Ny as the 2, in that case the energy it will become 1 by 4 plus of the 4. That means it is coming out to be 17 by the 4 into the h square upon the 8 Ma square. So this is if Nx is 1 and Ny is 2. If Nx is 2 and Ny is 1, in that case it will become 4 upon the 4 plus of the 1 into the h square upon the 8 Ma square. That means the energy is 2h square upon the 8 Ma square. So here you see this is 4 point something the value we will be getting in this case, and here it is twice of this h square upon the 8 Ma square. So this is gonna be the one which is of the first excited state. This will be of the first excited state, and this is gonna be of the second excited state. Second excited state. Now if the square box you were having, there these both levels which was 1 2 and 2 1, they were degenerate. But now in this case they are not the degenerate, their degeneracy has been lost. The lower one it is 2 1 and then it is 1 2. Right? For the lower one the energy we have got it 2h square upon the 8 Ma square. And here the energy value it was 17 upon the 4 h square upon the 8 Ma square. Right, so now for the first excited it is 2 1 h square upon the 8 Ma square, and degeneracy is 1 only. So you can see 2 1 and 1 2 they are non-degenerate. So for this again degeneracy is 1 only. Right, so based upon this you can see degeneracy 1 I can see in two of the options, but this energy we have got it, this is for the ground state. So this one was for the ground state. Right, and this is the one which is of the first excited state. So option A is the right answer in this. I hope it's clear. Moving to the next this question now. Choosing some Hamiltonian h and the orthonormal basis, a linear variation is carried out to get an approximate energy values which is Ej. Okay, with the two basis function. Two basis function it means the trial wave function that we have considered, it consists of the two of the functions like C1 phi 1 plus the C2 phi 2. This is the two basis wave function, and obtain the energies which is your E1, because the two basis function, so 2 is written in the bracket, and the second one energy it is E2, 2 it is there. Right, so here this is given that for these two levels the energies are of the order E12 it is the lower one and the E22 it is the greater one. Right, now take a three basis function, a new wave function which is suppose the psi t, a new trial function which is the dash we are proposing. So for this three basis function has been considered, which is C1 dash phi 1 plus the C2 dash phi 2 plus of the C3 dash phi 3. So this is the one. Here again the energies they have calculated and have got that the first level that you are getting the energy which is of the three basis function, this energy is smaller as compared to the energy which is of the second level where the three basis function we have considered. So these levels they are looking like this, E13 and it is the E2, considering the three basis function. So among these energies, the relationships we have to tell them. So what we know is higher the number of the variational parameters we include, more is the energy that is gonna lie close to the exact value, right? So this thing you know that higher is the variational parameters, higher is the variational parameters, parameters, more close is the energy, more close is the energy to the exact value, to the exact value. Now for the trial wave functions, the energy values as compared to the exact one, it is always the more. Okay. One more thing, keep in mind that the energies of the same states have to be compared. The energies of the energies of the same state are compared. The same state energies has to be compared. What it means, suppose I am taking this first level where the 3 basis function I am having and the first one where the 2 basis function you are having. This energy value, suppose the exact energy it is the E1 I am having. Now as compared to the E1, energy is gonna be more for the trial wave functions. So the one in which the 3 basis function you are having, that energy is gonna be the more, just slightly close to the exact, it is 9, and then the maximum one you are going to conceive you will be having where the 2 basis function you have obtained it. So this I have assumed to be the exact value, right? So what relationship between these levels we are observing, that for the ground state, the one in which the 3 basis function it is there, their energy it is gonna be less than or it is equal to the one in which there is 2 basis function you are having it, right? So this relationship it is gonna be hold, right? In the similar way, if you compare this levels which is of the E2, there again you will be having the one in which the 3 basis function we are having, their energy is gonna be lower as compared to the one in which the 2 basis function it is there. Like this you will be having the E2 which is of the 3 basis function, this is gonna be lower or equal to E2 2. So this is the second relationship that we will be holding. Okay. So first is saying E1 and the 2 basis function that you are having, that is smaller, and for the 3 basis function is more. This is the incorrect. Next, for the one with the 3 basis function and with the 2 basis function, for the 2 basis function it is more as compared to the 3 basis. This is the correct. Next, the second states has been compared. In this they are saying the third basis, the one with the 3 basis function it is gonna be more. Again this is the incorrect, right? Here it is saying for the first state only, the second, the two basis function, their energy is smaller as compared to the 3 basis function. Again, the incorrect one, right? Next, it is the first state only, the one with the 2 basis function, their energy is more as compared to the 3 basis function. This is the correct. Here also the second state has been compared, the one with the 2 basis function, their energy argue it is more as compared to the 3 one. This is also the true one. So option fourth, both these options that has been compared are the correct one. Okay. So these statements, they are just important, right? Next, the average value of the momentum for the ground state of a particle in a 1D box, it is 0. Why is it so? So what we have is the average value of the momentum that you have for a particle in the 1D box. This value it is equal to 0. Why is it so? Because this is suppose the particle you are considering having the length which is 0 to L, right? The potential inside the box it is 0 and the potential outside the box it is infinite. Now the particle it is moving like this, the particle it is going in this particular direction. So when it is going, it will strike back in this, it will strike to this particular wall and will be coming back in this direction, right? So that means particle is moving in all the directions it is moving, and the momentum that we have it is your vector quantity. It is your vector quantity. It has both the it has both the magnitude as well as the direction. It has magnitude as well as the direction. So what we see is that that due to the change in the direction, the momentum in all the directions it gets cancelled out. So momentum it gets cancelled cancelled in all directions, in all directions. So why is it happening? Because the state that you are considering, it is bound state we are having. Because of this boundary only this thing is happening. Had it been that this wall it is not present, it is not there, then the particle will not be striking with it and it is free to move in that scenario, right? So because the state it is bound, state is bound, this scenario it is possible. So momentum average it is 0 because the state is bound and is stationary. Option D is the right answer. Okay. Next, this one, for a Hermitian operator. First thing is Hermitian operator of A, which means the A dagger. If I am taking this is equal to the A only, which does not commute with the Hamiltonian. That means the commutator of this, this commutator of the Hamiltonian with this operator A, if I am taking this value, it is not equal to the 0. That means the HA, it is not equal to the AH. Right? This is what we are getting. It is not commuting with the Hamiltonian. Let psi1 be the eigenfunction of the A. What does this mean? The eigenfunction of the A. So if the operator A is applied upon the wave function psi1, it is gonna give me a constant, which is suppose the A eigenvalue it is giving me, and the wave function psi1 as it is giving me. Right? So in the form of the bracket notation also you can write it. This value here the psi1 value. So this is gonna give me the A psi1, the wave function as it is. And if I consider the bra notation of it, here the A operator, it is gonna give me the eigenvalue that is gonna look like this. Here the A star it will be there. Right? And psi2 they are saying it is eigenfunction of the Hamiltonian. What it means? Now on the Hamiltonian operator, if it is applied upon the wave function psi2, so this one we can consider like this. This is gonna give me the eigenvalue which is gonna be the energy in this. So we are getting the energy like this. And here in the ket notation, bra notation, if you see the Hamiltonian, if you are applying the wave function psi2 and the energy value you will be getting. This is what it means. The correct statement regarding the average value of the commutator of the A with the H. So commutator of this A with the H, its average value we have to find it out. So how do we find the average value of any operator? So now here the operator is this commutator value, right? So this we write it as the wave function as it is. Then you place the operator, that is A with the H, like this you apply it, and then the wave function in the ket notation. This is how we write it. So now just solve it. It will become the psi1 times the AH minus of the HA. This is what the commutator it means. I have just opened it, and the wave function psi1 as it is. This is what we will be getting. Now open this again. So we will be getting, so here it will become psi1 AH applied over it, and then the psi1 as it is minus of the wave function which is the psi1, and then the HA, and then the psi1 as it is. So now you see here we can apply this value. We already know that if the Hamiltonian was applied upon the psi2, but this value we know the psi1 and the A value. So here you see psi1 and the A value you are having, this one you are having, which is giving me this particular value, right? So this is gonna give you psi1 A star Hamiltonian and the psi1 minus of, here you again know this value. Now A into the psi1 value you are knowing, this is gonna be A and the wave function psi1 only. Now A they have said that it is your Hermitian operator. That means it is giving me the real eigenvalues. Now A operator, it is the Hermitian. That means it is gonna give me real eigenvalues, which implies the A star value, this is gonna be equal to the A only. So this condition if we impose, it will become psi1 A H and the psi1 as it is minus of the psi1 H A and the psi1 as it is, right? So A becoming the constant will be coming outside. So we are left with the psi1 H and the psi1 minus of the psi1 H and the psi1. So this is what it is becoming. So these both are the same values only. So overall it is coming out to be 0. That means if the commutator operator is applied upon the wave function psi1, I am getting the average value as 0. Right? In the similar way on the wave function psi2 also we can find it. So here the average value it will become psi2. The commutator of this A and the H, and then the wave function psi2 will be having, just open this psi2 AH minus of the HA, right, and then the psi2. So here it is becoming psi2 AH into the psi2 minus of the psi2 HA and the psi2, right. So here this the Hamiltonian is applied upon the psi2. So this give me the energy value and the wave function psi2 as it is. Here the operator A it was there and the psi2 we are having as it is. Minus of. Now psi2 applied, psi2 and this Hamiltonian in the bra notation of it, it gives me the psi2 and the E energy and the operator A and the psi2 as it is. Now again we know that Hamiltonian operator is Hermitian. It is the Hermitian, that means it gives us the real eigenvalues. Real eigenvalues, which implies the value of the energy, which is the E star here that you were getting. E star, it is equal to the E only. So again impose this condition now. So it will become the psi2, the operator A into the E into the psi2 minus of the psi2 into the operator into the energy, which was E star, it will become the E only into the operator A and the psi2 as it is, right. So now this E values it is coming outside, so it will become psi2 operator A and the psi2 only minus of the energy into the psi2 operator A and the psi2. So it is energy coming outside, again psi2 operator A and then the psi2, right, minus of the psi2 operator A and the psi2. So this is what we are getting. So again this is coming out to be 0 only. So that means the average value which the of these, if on the psi1, this average value of this commutator, that is AH, if you are observing on the psi1, this is equal to the one which is when applied upon the psi2. So I am a commutator of this operator, this AH on the psi2. This both are 0, right. So options, if you see in this, it is saying both of this they are non-zero, it is incorrect. Only this is 0 but this one is non-zero, this is again the incorrect. Only this is 0 but psi1 value is non-zero, again the incorrect. Both of this they are 0, option D is the right answer. Proof is there in front of you. Okay, next this question now. So this is from the again the CSIR June 2016. It says the ionization energy of the hydrogen atom in its ground state is 13.6 electron volts. So firstly is for the hydrogen atom. The ionization energy it is given 13.6 electron volt. This relationship you should know that the ionization energy it is a negative of the total energy of the system. So that means here the energy it will become minus of the ionization energy. So energy for the hydrogen atom it is coming out to be minus of 13.6 electron volt of it. Right? So this is the energy in this. So energy for the hydrogen atom we have is minus of 13.6 into the z square upon the n square. This value it is equal to the minus of 13.6 electron volt as per the given one. Now for the hydrogen atom the z value is the 1. So minus of 13.6 upon the n square it is minus of 13.6 only. So that means n square value it is 1 in this. Right, this is what we are getting from here. Now same from the for the helium atom I have to find it out. So helium positive, z value will be 2, n value will be the 1 again. So energy it will become minus of the 13.6 into the z square upon the n square of it. So minus of 13.6 into the 4. So it is becoming 6 4s are is 24, 4 3s are is 12 plus 2 it is 14, 54.4 minus of this electron volt you are getting. Now read the statement again. The potential energy of the helium positive in the ground state is approximately. So we are not asked the energy, we are asked the potential energy in this. So here the role of virial theorem will come into the play. Here the real theorem will come, according to which 2 times the kinetic energy it is equal to B times the potential energy, where B is the power of the positions that you have. So in the hydrogen atom systems, the potential energy we have, which is your Ze square upon the 4 pi epsilon naught into the R. So potential is proportional to R raised to the power of minus of 1. So B value is minus of the 1 in this. So that means 2 times the kinetic energy is minus of the potential energy. Now the total energy of the system, it is sum of the kinetic energy and the potential energy. Right? It is sum of the kinetic and the potential. Total energy we have found it, which is your minus of 54.4. Now the potential energy I have to find it. So write the kinetic energy in terms of the potential energy, which is your minus of the V upon the 2 plus of the V. So this is becoming the V upon the 2. So that is equal to energy, which is your minus 54.4 electron volt. So potential energy we are getting, which is your minus of the 108.8 electron volts of it. So this is gonna be the answer in this. Okay. So make sure you read the statements very carefully. Here you see the option of minus of 54.4 also it is there, but in the question it was potential energy was asked, so that means this is not the correct. D option is the right one. Okay. If sometimes you make a mistake of not reading the statement carefully, you might be thinking that for the helium atom in the ground state energy only it has been asked, then you will be marking the option A and it will give you a negative marking clearly. Right? So read the questions very carefully. Moving to the next, it is saying in a simple molecular orbital theory of the hydrogen molecule. So firstly it is the hydrogen molecule. So how do we form the hydrogen molecule? So two of the atoms you have it. This is the atom A, He, and this is the atom B, Hb. They are nucleuses and two of the electrons these are present in it. Right? Here the bonding and the anti-bonding. How do we form the bonding orbitals? Bonding means when the same loops they are overlapping. That means same phases of the orbitals they overlap. So 1s orbital if you consider for the hydrogen atom A, it's 1s orbital. The positive phase it is overlapping with the 1s orbital of the hydrogen atom B, again in the positive phase. This is gonna give you the bonding molecular orbital, where the increased electron density of the positive one we will be observing. So this is the sigma G that has been formed. Why it is called as the G ray? Because if you sit at the center of it, here also the positive charge density it is there. If you go on the left side, the positive density you are encountering. On the right side also the same phase you are encountering, which means that it is G rayed in the nature. Right? Whereas the anti-bonding, if you see, that is sigma ungraded. So how that we form it? One is the positive phase and other is the negative phase, which is overlapping. So if these two overlap, it gives the formation of the loops, which looks like this. Here there is positive and there is this negative one. In between these two, this is the nodal plane. This is the nodal plane. Right. So now it is unzeroed because if you sit at the center of the molecule, center of this orbital that you have formed, here on this side negative phase you are encountering, and here this is positive. So it is the unzeroed in the nature. So this is the anti-bonding molecular orbital which has been formed. Okay. Now next, there have been sigma G and sigma 2U are constructed by the linear combination of the atomic orbitals of two of the hydrogen atoms. The spatial part of it, it is purely covalent. Purely covalent, we have to find it. Singlet wave function is obtained by which of the following scenarios? So we should firstly know. So you see here in the terms of sigma g and sigma u, it has been given. So from the linear combination, we can see that sigma g would have been formed if the positive lobes are overlapping. So the phi A, which is for the first electron we are considering, that is of the atom A, it is overlapping. So positive it is written with the phi B of the first electron of the other atom B, right? And the sigma U would have been formed if the phi A1 is overlapping with the negative phase of, so minus it is coming, of the second atom, second B atom containing the first electron. So this is sigma G and sigma U. Now we need is sigma G2 and the sigma U2. How we will be finding that? Sigma G2 plus of the sigma U2, their square it is given. Sigma G2, it will become, that is your phi A1, it is your phi A1 plus of the phi B1. Now the second time again sigma G we have to consider, that is for the second electron. So it will be again phi A2 this time plus of the phi B2 now, right? Plus of the sigma U, that is gonna be for the first electron it is phi A1 minus of the phi B1 into the phi A2 minus of the phi B. So this is gonna be there. Now just open this. It will become the phi A1 into the phi A1, phi A1 into the phi A2 plus of the phi B1 into the phi B2 plus of the phi B1 into the phi A2. Just the simple multiplication that we do, that is what we are doing over here also. Phi B1 into the phi B2, right? Plus of. Now the second one, it will become phi A1 into the phi A2 minus of the phi A1 into the phi B2, right? Minus of the phi B1 into the phi A2 plus of the phi B1 into the phi B2. So this is what we are getting. So now here you see it is phi A1, phi A2. Here also it is phi A1, phi A2. So both of these are of the plus. So it will become 2 times the phi A1 into the phi A2 of it. Similar way, if you see now, it is phi B1, phi B2. Here it is minus of the phi A1, phi A1 and the phi B2. So it is phi A1. Where is that? Here it was phi A1 and the phi B2. So this value is of the positive, this is of the negative, so these two gets cancelled. Here it is phi B1 and the phi A2, phi B1 and the phi A2, this also it is getting the cancelled. So this value now phi B1 into the phi B2, both of this they will be again 2 times of it. So 2 times the phi B1 and the phi B2 we are getting it. Now what does this, the total wave function is implying? So first electron it is on the atom A, the second electron is on the atom B. That means both these electrons, which is 1 and 2 on the atom A, that is it is your ionic part, right? Here also the first electron on the atom B, the second electron on the atom B, again the ionic part it is representing, which means the sigma G2 plus the sigma U2 it is representing the purely ionic character. Purely ionic. We needed is the purely covalent one. So that means option A is the incorrect. Next, if you see sigma G2, if you see, so let's do that. Next it is sigma G2. So it will become the phi A1 plus of the phi B1, right, into the phi A2 plus of the phi B2. So for the second and the first electron, open this. It will become phi A1, phi A2 plus of the phi A1 into the phi B2 plus of the phi B1 into the phi A2 plus of the phi B1 into the phi B2 of it, right? So here if I see the phi A1 into the phi A2 plus of the phi B1 into the phi B2 plus of the phi A1 into the phi B2 plus of the phi B1 into the phi A2. So what it is representing to us, you see the first electron on the atom A, the second electron on the atom B. So it is the atom A only it is there. So both the electrons on the same atom, it is representing the ionic part. Again the first electron on the atom B, second electron on the atom B. So both of these are on the same. So again it is the ionic part. Here if you see first electron on the atom A, the second on the atom B. So this is representing the covalent one. Here, first electron on the atom B, the second on the atom A. So it is again the covalent character. So this sigma G2 that you are having, it is mixture of the ionic and the covalent. Ionic and the covalent. So again not the pure covalent bonds we are getting. So again this can't be the answer. So option B also is eliminated in this. Right. Now the third is sigma G2 minus of the sigma U2. Let's do that. It is sigma G2 minus of the sigma U2. So this it will become phi A1 plus of the phi B1 into the phi A1, phi A2 plus of the phi B2, right? Minus of this, which is the phi A1 minus of the phi B1 into the phi A2 minus of the phi B, right? So this values, now open this, it will become the phi A1 into the phi A2 plus of the phi A1 into the phi B2 plus of the phi B1 into the phi A2 plus of the phi B1 into the phi B2. So this is what we are getting, minus of. Now open the next one. It will become the phi A1 into the phi A2 minus of the phi A1 into the phi B2 minus of the phi B1 into the phi A2 plus of the phi B1 into the phi B2 of it. This is what we are getting. So here you see this value phi A1, phi A2, it is positive. Now whole of this bracket will be multiplied with the negative sign. So phi A1, phi A2 is of the negative. So these two it will get cancelled out. Similar way, the phi B1 into the phi B2, this is positive. This will, after multiplying with the negative sign, will become negative. So these two gets also cancelled out. So we are getting is 2 times the phi A1 into the phi B2 plus of the phi B1 into the phi A2 only. So this is what you are getting. It is implementing the first electron on the atom A, the second electron on the atom B. So covalent because sharing of electrons is done. Here also first electron on the atom B, the second on the atom A. Again the covalent character you are having. So both of these are the covalent. So it is representing the purely covalent bonds. So the correct option will be the option C in this case. Third one, that is representing the purely covalent wave function. Okay. This is how this type of the question has to be solved. Right. I hope it's clear. Next. Again, now it is CSI December 2016. The correct normalized wave function for the sp2. A similar type of the question we did, that was for the sp hybrid orbital. Now it is sp2, right? That means percentage s character in this, it is 1/3, and the percentage of the p character, if you see, it is 2/3 of the 100%, right? That means S character is 33% and the P character it is 66%, right? Also this wave function has to be normalized because three components they are including. So wave function, triangle wave function, it will be of the type C1 phi 1 plus the C2 phi 2 plus the C3 phi 3, it is there C3 phi 3, their squares, which is C1 square plus the C2 square plus the C3 square. This should be equal to the 1. That means the wave function should be normalized, and this condition, which is percentage of the S and P, it should also be satisfied. right? Now the first option, if I take, it is 1 by 3 minus of 1 by 3 and 1 by 3. So the square of it, if I take, it will become 1 by 9 plus of 1 by 9 plus of 1 by 9. It is becoming 3 by 9, which is becoming 1 by 3. This is not equal to the 1. So here the wave function is not normalized, so incorrect, right? Option B, if I see, it will become 1 by 3 plus of the 4 by 3 plus of the 1 by 6. So it is becoming 2 plus of the 8 plus of 1 upon the 6 it is becoming. So this is becoming your 11 by the 6 it is becoming. So it is not again equal to the 1 over here, right? Next, the C option, if I see, it is becoming 1 by 3 plus of the 1 by 2 plus of the 1 by 6. So it is becoming 2 plus 3 plus 1 upon the 6, that is 6 by 6, which is equal to the 1. So my wave function, it is normalized. So that means this one I can take into the consideration. Here also in this I see it is 1 by 3 plus of the 1 by 2 2s are 4, 4 into the 2 will be 8 plus of the 1 by 6 it will become. So take the LCM again. So 8 into the 6 we can consider. So it will be multiplied by the 16 plus of the, now here this 6 and this it will be the 8 upon the 8 into the 6, which is your 48. I am taking it. Okay, so this is becoming the value, which is 6 plus 8 is 14. 14 plus 16, it is becoming the 30 upon the 48, which is not equal to the 1. So it clearly implies the normalized wave function only, it is the option C1, right? Now one more way you can check the percentage of the s character also. So it is the 2s orbital in this, right? So C1 square value that you are having, it is 1 by third of it, right? So 1 by third of the percentage if I am considering, so it is coming out to be 33% only. Whereas the p orbital's contribution, if you will be seeing, overall you will be getting it to be 66% only. So it clearly implies that this is my sp2 hybrid molecule. Orbital it is there. Okay. Next, again CSIR December 2016. The orbital degeneracy of a level of the one electron system with the z value equal to the 5 and the energy value as minus of 13.6 it is gonna be. So degeneracy we know it is equal to the n square value of it. The energy value it is minus of 13.6 z square upon the n square. This value is given to us, which is minus of 13.6 electron volt. Now z value is 5, so just substitute that. It will be 5 square over here upon the n square, which is equal to minus of 13.6. These gets cancelled on both the sides. So n square it is equal to the 5 square only, which is your 25, and this is nothing but the degeneracy. So degeneracy is 25 in this case. That makes the option C to be the right answer. Okay. Next, if we write the normalized wave function, which is psi into the A into the phi here it's also there, then the phi will be normalized when which of the conditions is satisfied. So the wave function psi, it is A into the phi. Now here the psi, it is normalized. It is given to us psi is normalized, which means integration of the psi star into the psi into the d phi, it will be equal to the 1 only, right? Now the wave function, it is A into the phi, the conjugate of it, into the A into the phi into the d phi, it is equal to the 1 only. And now it is becoming the A star into the phi star into the A into the phi into the d phi. This integration is equal to the 1, right? So A star and the A, I am taking it outside. This is phi star and the phi is equal to the 1. Now the condition we have to apply, that phi is normalized. Phi is normalized, which means integration of the phi star into the phi into the d phi, it should be equal to the 1 only, right? It should come out to be 1. That is the value of the A star into the A, it should be equal to the 1, then only this condition it will be satisfied, right? Because if this thing it becomes to be the 1, then this scenario it will be possible, right? So that means A value, it should be a unitary, it should be unitary. It should be unitary. That means the one value it should be having, only then this condition will be satisfied. So based upon this, option C will be the right answer. Okay. Now moving to the next one. In this question, the ground state of a certain system with the energy which is E0. So we are having the system whose ground state value is given. It is E0. E naught it is, or the epsilon naught you can say, is subjected to the perturbation which is V1, yielding the first order correction which is the E1. So E1 they have applied, which is the first order correction. This is your first order correction. If E0 is the true ground state, if E0 is the true ground state energy of the perturbed system, the inequality that holds good in this case. So here we know that the energy E0, it is of the true ground state means the exact value, exact ground state energy. So the trial wave function energy, it is always gonna be more than that of trial wave function energy is more than the exact wave function energy is more than the exact, right? That means E naught value that you are having, this is gonna be less than equal to, now the perturbed system energy, it is gonna be E naught plus of the E1. This is the perturbation plus the energy which is of the ground state, that of the perturbed system that they are obtaining. This E1 value that you are having, which is the perturbed system energy, it can be either the positive or it is always the 0. For the ground state we are seeing, so for the ground state it is always the positive or it is the 0. That is why the symbol which is less than equal to has been imposed over here. Right? So this scenario of the energy you are gonna observe. First is saying first order perturbation is greater than equal to the 0. This is true, but with the comparison with the energies we have to compare it. So overall this is not the most opt one. Right? Next, E naught value, it is more than that of the ground state energy. So again the incorrect one. The option this is saying that the ground state energy, it is more than that of the perturbed system. This is again the incorrect. Here it is saying the system E naught that you are having, in that the perturbation that you have applied, this value is greater than equal to the ground state energy, true exact value that you are having. So option fourth one is going to be the right answer. Okay. Next, this question now, the spatial part of the excited state, which is B for the system, which is the triplet state, it is given sigma u plus it is given of the hydrogen molecule, it is proportional to. So here the system it is given, we are having the 1 sigma g 1 sigma u 2 it is given minus of the 1 sigma g2 and the 1 sigma u 1 it is given. So using the linear combination of the atomic orbitals, molecular expansion of the sigma 1g and sigma 1u, in the terms of the 1s atomic orbitals, one can infer the wave function it is having which of the parts, whether it is containing the only ionic parts, covalent, or the mixture of this, or neither the ionic or the covalent. So now I know that sigma g1, so for the first electron it will be phi a1 plus of the phi b1, because hydrogen molecule is again given, so 2 atoms and 2 electron system it is there. Sigma g2 it is gonna be phi a2 plus of the phi b2, right? Similarly the sigma u1 it is gonna be phi a1 minus of the phi b1, and the sigma u2 it is equal to the phi a2 minus of the phi b. So now the given wave function, in that you just have to apply these expansions. So the wave function is sigma g1 This is the sigma G1 into the sigma U2. So minus of the sigma G2 into the sigma U1. So sigma G1 it is phi A1 plus of the phi B1, right? Sigma U2 it is phi A1 minus of the phi B. Sorry, for the second electron it is the phi A2 minus of the phi B2, right? Minus of sigma G2 it is the phi A1 plus of the, for the second electron, so phi A2 plus of the phi B2 it will be there into the sigma U1, so phi A1 minus of the phi B1, right? So now just open this, we are getting the phi A1 into the phi A2 plus minus of the phi A1 into the phi B2, okay, plus of the phi B1 into the phi A2, right? Phi B1 into the phi A2 minus of the phi B1 into the phi B2, right? Minus of this, which is your phi A2 into the phi A1, right? Minus of the phi A2 into the phi B1 plus of the phi A1 into the phi B2, phi A1 into the phi B2, and minus of the phi B1 into the phi B2. So this is after the expansion we are getting. So you see phi A1, phi A2, this is of the positive. This value which is phi A2 into the phi A1, this is negative. So these two will get cancelled out. Similarly, the phi B1, phi B2, this is of the negative. This negative will become positive. So this is also getting being cancelled out. So we are left as with 2 times the phi A1 into the phi A2 plus of the phi B1 into the phi A2. So we are left as with 2 times the phi A2, phi B1 minus of the phi A1 into the phi B2. So you can see it. This term you were having, this is of the phi B1, phi B2, this is of the plus phi B1 into the phi B2. This negative will become the positive, and here this one was of the negative. Here also it will become the negative only, right? So this value you are getting. So what it is representing? The first electron on the atom B, the second electron on the atom A, the first electron on the atom A, the second electron on the atom B. So this is representing the covalent character, and this too is representing the covalent character only. So purely covalent wave function it was given to us, right? So that makes the answer to be only the covalent parts are present. So option B will be the second one will be the right answer. Okay. Next, this question now. Two boundary stationary states 1 and 2 we are having of the one electron atom with the energy E1 and the E2. So two states you are having. So this is the state 1. This is having the energy which is E1, and this is the state 2 which is having the energy that is E2 we have been given to us. E is the total energy. Obey the following statements about the kinetic energy and the potential energy. So relation between the kinetic and the potential we have to find it out. That how can we do? With the help of the virial theorem we can do this, right? And the system is of the one electron atom. That means about the hydrogen atom. The relationship that we have to see between the kinetic energy and the potential energies, right? So according to the virial theorem, right? 2 times the kinetic energy is V times the potential energy of it. The potential energy is Z E square upon the 4 pi epsilon naught into the R. So V value is proportional to R raised to the power of minus of 1. So B value is minus of 1. 2 times the kinetic energy, it is minus of the potential energy, right? So this is in the state E1 that you are having. State 1, the energy E1 that you are having. This is the sum of the kinetic energy T1 plus the potential energy V1 in it, right? Now here the value in terms of the kinetic energy only if I am finding. So here the potential energy is minus of the 2 times the T1 it is there. So this is T1. The total energy in terms of that it will become the minus of the T1. So this is the energy energy E1 which is equal to the minus of the T1 of it, right? And the E2 value that you are having, this is also gonna be sum of the kinetic energy plus the potential energy. The kinetic energy in terms of that if I'm finding, so T2 minus of the 2 times the T2. So this is the value E2. So E2 value it is minus of the T2. So here a condition it was given in the statement that the E2 value that you are having it is more as compared to the E1. E2 value is more as compared to the E1. Based upon this, you need to compare now the kinetic and the potential. So it is given that E2 is more than that of the E1, which implies minus of the T2 value. This is gonna be more as compared to the minus of the T1 of it, right? Or we can say that because here the negative sign is placed, or the T1 value that you will be having, it is gonna be more as compared to the T2. T1 will be more as compared to the T2. So you can see here that here it is suppose the minus of the 5 minus of the 5 you are having, and here is minus of the 7. Minus of 5 is more than that of the minus of 7, and we know that 7 is more as compared to the 5. So this concept is used over here. So relationship between the kinetic energies of the two states is T1 is greater than that of the T2. Based upon this, if I see here T2 is greater than the T1, incorrect. T2 is greater than the T1, again the incorrect. T1 is greater than that of the T2. Option C will be the right answer. Right, here also T2 is equal to T1, that is also the incorrect. So option C will be the right, but you can also find the relationship between the potential energies in the similar manner. So E1 value it was T1 plus the V1 of it. Now the V1 value it will be minus of the, in terms of the potential, now I have to write it. So it will be minus of the V1 by the 2 plus of the V1. So we are getting V1 by the V2. So this is the energy E1. Similar way, E2 value that you will be seeing, it will be V2 upon the 2. Now E2 value it is greater than that of the E1, which implies V2 upon the 2. This is gonna be greater than the V1 by the 2, or V2 is greater than that of the V1, right? So here V2 is greater than the V1. Option C, it clearly becomes the right answer. Okay. So this was the last question that was to be discussed in this part. I hope all the questions that we have discussed in this part, they are clear to you. So thank you so much for watching. I'll be meeting you in the next video where the further questions we will be discussing. Okay, and if you have understood the concepts of this video, make sure you hit the like button for the video and do share it with your friends as well. And if you have not subscribed to the channel so far, make sure you subscribe to the channel also so that you can get the notification for the upcoming videos too. Okay, so thank you so much. We'll be meeting you in the next video now.